Yeah, I got it working.
Does it work? Okay, cool.
I don't know if this though. Test. Yep, now it works.
You have a laser on it as well, too.
Oh, in here?
So if you want to point anything at
Test.
Oh, I see it.
Okay, good morning. We're going to start the last session of Hot 3D with two speakers today. One is One is Chris Steinberg. He's up first, and Chris is a tools engineer, and he's working on graphics and graphics adjacent problem domains. And he's now at Samsung, and he's the lead engineer on the SOHCAHTOA graphics profiler, and this is the topic of his speech as well. Okay, thank you. Take us away, please.
Good morning, everyone. My name is Chris Steinberg. I am a senior staff engineer at Samsung Austin Research Center, and I work on the GPU developer tools team. Samsung Austin Research Center is also known as SARC. We develop the Exynos graphics chipset as well as the Vulkan driver that's associated with it. We also develop and maintain the tooling infrastructure for Samsung's Android graphics hardware. Today I'm going to take a look at one of those tools, SOHCAHTOA. This is one we built in-house. SOHCAHTOA is a multi-frame graphics and graphics profiler. It supports capturing Vulkan on any Android device, not just the Exynos chipset. It also supports frame debugging and shader modifications and replay. You may be wondering why we called it SOHCAHTOA, and if you're a math enthusiast, you'd be right to assume that we took inspiration from the trigonometric identity, because, well, graphics is mostly all about triangles. So why did we develop a graphics programmer, another graphics profiler? The Vulkan ecosystem does have some great tooling. However, it was missing a tool that was really tailored for Android. AGI was deprecated by Google a few years ago, and we needed something to support modern Vulkan. Every hardware vendor has tools specific to their hardware, and this does work great for IHVs, but it's not really user-friendly for app developers. It typically means you have to learn multiple tools, and many tools also specialize in either performance or debugging, not really both, which again means learning multiple tools, and even worse, you have to typically map data between them, particularly events, and possibly over separate captures, so not even really the same data sets. And this is difficult for analyzing temporal issues in your application, things that may happen sporadically. We use GFXR as our backend, and we collect multiple data sources, both GFXR and Perfetto by default, and that allows us to perform replays and recapture data on Android. You can, in SOHCAHTOA, also just choose to capture just Perfetto or just GFXR. We've designed the application to be very flexible to meet your tooling or capture needs. Data is the core of profiling, of course, and we've designed SOHCAHTOA to be extensible as well. So for hardware vendors that have different data sources other than GFXR, or application developers that may want to collect other data, it is possible to extend SOHCAHTOA to perform those activities. SOHCAHTOA was primarily developed by SARC, but it was in conjunction, in partnership with both Google and LunarG. You can download SOHCAHTOA today at this barcode or this URL. We've released twice this year, and we do plan on releasing twice more before the end of the year. I also gave a more in-depth demo of all of the core features of SOHCAHTOA at Vulcanize 2025. Here's a link to that video you can take a look at. When I gave the presentation, we hadn't really decided on what we were going to call the application yet, so there is no branding, unfortunately, in the video, so it makes it kind of hard to find if you're just searching YouTube. So I'd recommend using this link. So now I'm going to talk about some of the upcoming features that we are working on. My team is very proud to share these with you today. The first is ShaderQ Thread Trace, also known as SQTT for those in the know. This is additional data sources that are supported by the Exynos chipset, and it can provide highly detailed information such as draw event timing, wavefront occupancy, shader instruction timing, and ISA shader representation, also known as shader assembly that you see here. In this image, you can see the ISA code of a vertex shader being shown. This is pulled directly from the device and not compiled using an offline compiler, which is important when you're trying to actually do detailed instrumentation. SQTT data is extremely important as Perfetto itself does not provide enough detail, even on Exynos chipsets, to measure per draw event timings without serializing the events using a Vulkan layer, which comes with its own set of complexities, as was covered in Simon's talk earlier on Friday. With SQTT, we can provide an event timing view that shows detailed event level durations and additional information such as the number of wavefronts and threads that were executed in each shader stage for every draw. This can also tell you the register pressure of each shader stage based on the architectural's ISA compilation and not just an estimate based on SPIR-V intermediate code representation. And note that this is still in development and currently requires rooted devices, which is unfortunate, but we are working on trying to get SQTT data into production devices. But in the meantime, we are going to start exposing this to partner companies that have access to engineering reference devices. So if you have that or if you're interested, please reach out to us for information. This is being developed as an extension to SOCOTOA, so other hardware vendors that have similar data should be able to contribute their data to populate these views as well. And we will be releasing more detailed information on extensions and extension development sometime in the near future. And we would love to discuss extension requirements with other hardware vendors that are interested in contributing. The next tool I'd like to talk about is our extremely powerful AI analysis support. This will provide your LLM with access to profiling data, including Perfetto and GFXR, along with pre-designed skills to assist in quickly and efficiently analyzing those data sets. It uses a bring-your-own LLM approach, so you can use whichever model you prefer, including local models. And it will work with any capture from any architecture, not just Exynos devices. So what are some use cases you might use this for? Here's a list that I've included, but it's really not limited to this. You can quickly find jank frames in your scene capture, determining what CPU resource operations are likely the cause of your drop frames, analyzing counter data for insights as to why your GPU submissions are executing slowly. You can analyze resource configurations to get suggestions on how to improve performance, such as texture formats, compression, dependencies, and synchronization. Analyze shader code to identify areas of optimization, such as load store patterns, and many others that I'm sure you're all thinking about while I'm reading the list here. So I'd like to show you how this works in action. I do apologize if some of you in the back might have difficulty seeing it, since it's a lot of data and the text is going to be kind of small. Yep, okay. So first, we're going to open our chat panel, which should be a very common action for many of you who use VS Code AI harnesses. Then we will ask our configured LLM to analyze our capture. This is a capture of one of our bad games demo scenes, and we use it to highlight typical performance issues. The LLM gets to work and provides us some high-level statistics and our top 5 worst performing frames. It also provides bottleneck analysis and some critical findings, including that our stutter and jank was caused by large image uploads, which is what the scene was really intended to showcase. Next, we asked it to give us details on the resources used in the slowest frame. So, let it catch up here. It tells us that we are uploading 100 textures, or about 400 megabytes, on a single frame, and that all of the textures are uncompressed. The fix here should be pretty obvious. We should add compression and space out texture loading across multiple frames if possible. The AI also provides us useful links to quickly navigate and locate to the location in the capture that caused the source of the slowdown. This feature really greatly speeds up the time from capture to identifying the key issues you need to discover and improve your application's performance. It alleviates the tedious sifting of data to find issues that can give you insights into your application maybe you didn't even know. So I think that's pretty great. It definitely improves performance optimization planning. We are planning on releasing the AI feature as part of our 1.1.0 release in August, and with improvements for refining the base skill set and token consumption throughout the rest of the year. So thank you, HPG, and I hope you run SOHCAHTOA on your demos. You can also join us on Discord, where you can ask questions and provide feedback directly to my team, and we look forward to hearing from you.
All right. Are there any questions, Chris? I think it may make sense for you to step down from the lectern and use the other mic, because this thing really makes it impossible for you to hear anything.
A great talk. The AI analysis, is this a repeatable analysis? Is it backed up by scripts that it runs and then uses to sort of show you the hotspots or highlights or whatever? How does that work?
Yes, we have a set of skills that we built up that include access to pre-canned SQL-like queries and functions that we built to kind of do some of the heavy lifting on the analysis. But the LLM provides kind of the flexibility for you to ask more specific questions. If it doesn't have a skill set, it will just analyze it'll formulate its own SQL queries. It's still looking at the data directly. But we are expanding that skill set and kind of using the LLM to help us shape what those skills are going to look like as well. If it finds a better query and we get some good data from it, then we're capturing those local, in-house and analyzing them to make sure that we can expand our skill set.
Great. Is that something a user could do too until you guys refine it?
Yes, we have a skills configuration page inside of SOHCAHTOA itself where you can also write your own prompts, skill prompts in there, including SQL-like queries.
Okay, thank you.
Yep.
I couldn't read the assembly. Is it an intermediate language? Is it, the hardware-specific assembly? Can you see both? And how would plugins work for other vendors' assembly if it supports that?
Yes, it is the hardware-specific assembly, and it currently works for us by we pull the SQTT data, and that data is included in there. But the extension interface itself is kind of more piecemeal. So when the UI calls to request for ISA, if that extension supports delivering ISA information, then it's really up to the extension writer to determine how to pull the information and what version of the information to display. So as long as you provide a language schema for coloring, then you can we can color the ISA, do the markups on that as necessary.
If you have source and whatever, is there any way to map like HLSL to intermediate to ISA, or is you only get ISA? How does that work?
Not currently. I know that some compilers will include, like in SpearV code, the actual original source code, and we've talked about expanding support to do that mapping, but we don't currently support that yet.
Okay, are there any more questions? I have a question. So the thing I haven't quite, I guess, understood is the LLM running locally, or can you just use any
Yeah, it's configurable. You bring your own LLM. So like this was being ran through Claude so we were using an API key there, but it does have full AI configuration, so you can provide a different endpoint for your LLM model if that's local or one of the major providers.
Okay.
All right, thank you.
Thank you. Okay, so next up is Ben Watson. Ben is an associate professor of computer science at the North Carolina State University. He leads the Visual Experience Lab, and that focuses on the engineering of visual meaning, and it also works in the fields of gaming, graphics, visualization, interaction, and user experience. And Ben is going to talk about, I think, an outlook that he calls the game rendering manifesto. So I think it's going to be quite interesting. Okay, Ben. Thanks.
Just a moment while I set up. Here we go. All right. Yep. All right. Thanks, everybody, for coming today. It's a privilege to speak to you all. As Holger said, I am going to present a game rendering manifesto. So I'm going to be a little bit, I hope, not horribly, but a little bit provocative. And feel free to follow along using these links or QR code in my slides if you like. So here's a quick preview of what's coming, so short outline. First, I'm going to argue with some support that photorealism is mostly finished. We're largely done with it. And so what should we do next? I'm going to argue that we need to reinvest in game rendering, and I'll talk about what I mean by that. And then I'll talk about a few of the many challenges I think that poses, and some of the many, not as much as I would like, but some of the many research efforts that precede us today and inspire me in our lab. And then I'll conclude with sort of the broader impacts that this kind of effort could bring to fruition. So on to my first claim that we're mostly done doing photorealism. Let's start with a little bit of basic education. So Blind's law. Let's listen to, I have to go over here. Let's listen to Jim define it himself. So there's a little audio about to come. There you go. It says can't load the audio. My fault. Anyway, he just says what it says here. As technology advances, rendering remains constant. Oh, it's because I'm not networked. Okay. I should have checked that. Sorry? USC guest? Okay. Yeah, I'm trying. Do I need to log in or anything? Okay, try again. Still not hearing anything. But I'm not getting the error now. Let me try reloading. How about that? Yeah. Is there no sound coming out of the... Oh, okay. Yeah, I do. apologies. Okay. Backing up, trying again. Still not hearing anything. Definitely playing though. Okay. That's a shame. So Blind's law says that as machines improve, as compute improves, rendering time will remain more or less the same because we're just going to make our frames look nicer and nicer, right? And then for gaming, at least historically, what this has meant is that sort of 10 years later, we do the same thing, right? Lately, I think the gap is less, but we're sort of getting the hand-me-downs from, film and TV industries. So this is George Lucas from 20 years ago, and I'm guessing the audio won't play this time, but we'll try. There it goes.
Digital technology, digital cinema is now here. It's just slow in getting accepted, it's cumbersome, it doesn't always work as well as we'd like, it's got a lot of improvements, but they're mostly just, better knobs and whistles, a better place to put your coffee cup. It's not like we're going to reinvent the wheel. It's been reinvented now.
Mm-hmm. Okay, I'm glad we could hear that. So that's, as of 20 years ago already, George Lucas thinks we're mostly done. And I'm not sure this will work, but we'll find out. This is Jim Blinn, just a couple years ago, asked about photorealism.
And where is all this heading? Is the ultimate goal to make computer animation almost photorealistic or even better than reality, whatever that might mean?
Well, I think we've kind of arrived at that. I see a look at Pixar movies, and they look, and most of them are kind of cartoony in the sense that you're not going to mistake them for a real thing, but certainly a lot of stuff that you see in computer animation nowadays looks pretty photorealistic.
So I'm not sure how clear that was, but basically he was also arguing that we're mostly done, that graphics looks quite convincing outside of Pixar, where it's just not meant to look very realistic. And then what about gaming? So today, within the last several years, gaming CG has become good enough for movies, right? So because of the virtual production and in-camera effects, we have game engines being captured on film for high-end productions and becoming a virtual set. So essentially now we have at least some evidence, very practical evidence, that game graphics are good enough for the movies too. So what should we do now, given that the returns on photorealism are diminishing? Well, let's ask this question. What is realism anyway, right? So this isn't realistic, right? But this is not a problem that we encounter when we make TV or movies, right? Because there are two things here that are not present in any recorded media. One is that there's interaction happening, right? So there's the time in which the user is acting and the time in which the system is responding. And then there's some time difference between those two. So there's interaction and time that are variable here, right? And we're all intimately familiar with this. But if you think about it, this is, you know, the way reality works is not like this. So maybe we should begin thinking about temporal realism. And if we do, if we think about those two issues, gaming to support humans who are interacting with our real-time images, and delay trying to respond as quickly as we can, then we can begin addressing concerns that film and television and those doing CG for recorded media never had to, right? And we can begin to move away from sort of following in the path of CG for film and for other recorded media. And I'm not alone in arguing for this. So this is one of the most famous esports athletes in the world. This is Lee Faker Songhyuk. He's a League of Legends athlete. And he says, he claims, and he has good evidence for it, that he can feel differences as small as 5 pings. So for those of you who don't know what that means that he can notice 5 milliseconds of latency. Right? If you add 5 milliseconds, he can feel it in his gameplay. And then my colleague, Joseph Spute, there he is, and his colleagues at NVIDIA several years ago at SIGGRAPH presented some research that found that gaming performance, shooting in particular, certain kinds of shooting, continue to improve all the way down to 24 milliseconds of input to out to display latency. And that may not have been the floor, right? That was just as far as low as they could make their latency at that time. And then some work I did with one of my own students, who's actually going to present later at SIGGRAPH on Thursday. We found that, at least in Dota 2, many players reduce visual quality to improve latency, most, in fact. And in particular, let me turn on my highlight here. Here we go. So if you notice this part right here, 80% of the players turned off VSync to reduce latency. You know, they were quite willing to tolerate big visual artifacts like tears in the middle of their images to reduce latency. So that's actual positive action by these players. And even more recently, folks in the gaming media have begun to write about how all this photorealism may not be as valuable as we would like to think, right? Most gamers are still playing without ray tracing, and many AAA studios are not prioritizing it. So what does this all imply? I think what it implies is that we should be researching a little bit less about photorealism and a little bit more about recency, or perhaps temporal realism. And the term I would like to call that is low latency rendering, right? At least that's one direction we could be going now that photorealism is approaching peak. And even more than that, maybe realism isn't what we really want at all. So this is another esports athlete. I'm going to butcher his name, Michael Shroud-Grzik. I'll just read this to you. If you have high graphics, you see shadows, you see more stuff, but you see a bit more detail. But when a guy pops out of a corner, you don't need detail. You just need to see his head and his body. So he's basically arguing against more detailed, more accurate imagery. And NVIDIA, again, has put out a few products. This one's called Digital Vibrance. And this is a fairly simple version of it. What it does is take a standard game image, and then in a post-process, it ups the saturation, mostly. and this is in widespread use by a lot of competitive gamers. What it does is it improves the salience of the features you need to see so that players can respond more quickly. And I'm not an expert in Valorant, but Joseph tells me that some of this is already happening inside Valorant by design. So enemies are highlighted and fairly high contrast and simply rendered to make it easy for players to find and target them. So here, this is a different kind of game rendering research. So less worried about beautiful imagery, aesthetic imagery, more concerned with providing information, and in particular providing it quickly, making it very accessible to the player, to the user. And so I would call this informative rendering. So here are some of the challenges that these two directions, and I'm not claiming these two directions are exclusive. I totally believe there may be others. But here's some challenges for these two directions. And there's many more that I've thought of, and I'm not including them all here. But there's a draft, a preprint that goes with this presentation that we'll link to at the end of it with more of these challenges. All right, so one low latency challenge is object order rendering itself. By object order rendering, we mean we're rendering object by object or triangle by triangle. And what's the problem here? The problem is that as you're building a frame, as you're building an image, you don't know that you're done until you render the very last object or the very last triangle, right? Whatever you've rendered, any piece of it could be covered up and occluded by the last triangle. So that means that you can't present the information to the player, to the user, until some time has passed, right? And some time passing, that's latency, right? And that's what players don't like. The alternative would be some kind of pixel order rendering. And the obvious example, maybe the only example, there probably are a few alternatives, is ray tracing. And the difference here is that with a pixel order renderer, the last, as you render a pixel, that color is final, and theoretically at least, you could send it immediately to the display and to the player's eyes. And that would eliminate some latency. So how do we overcome that? That's a challenge. Frames themselves are a problem. So when we build a frame, we don't display it until the last pixel is finished. So that means every frame, and I'm not new in observing this, every frame is one frame time old before the user ever gets to see it. So that's, again, latency that we're introducing. And so the challenge here is, what could we do instead, right? And maybe this is more provocative even. So GPUs include a lot of these assumptions in their hardware design, right? So they include frames. They include, or at least primarily, are focused on object order rendering. They include other challenges. I'm just going to name a few more. Synchronization, which means waiting. Buffering, which means waiting. Scanning, which serializes and adds more delay. Those are just some examples. So if you want to do something different, it's challenging to do it with today's GPUs. And then the fundamental challenge in informative rendering is how to inform quickly. So I showed you some enhancements in contrast, some enhancements in saturation. There are tools out there for doing that, highlighting. This example is just one direction. I wouldn't say it's necessarily a realistic possibility, but psychological studies have shown that people people depicted in caricatures faster than they do in photographs. So that's just one example, but there's a whole range of perceptual and cognitive questions that could be examined in this challenge. So let's look at a few efforts in these directions. And the first one is not really research, but I'm including it because I'm so inspired by it. This is the Atari 2600, or the VCS, from 1977, so 50 years ago. Its latency, if you measured it, was 10 milliseconds, which is way below most of today's systems. And in a sense, they had to do that because shades of news these days, memory was super expensive back then. Frame buffers didn't really exist for that reason. And so they were racing the beam. They rendered a line at a time. And they had severe timing constraints, as you might imagine. But they solved them, and their system had extremely low latency, and we've rarely ever approached it since. So I find that sort of alternative architecture very inspiring. Much later, so Friston and his colleagues down in New Zealand built a system for VR, and they included they addressed several of the challenges I listed. Their system was able to reduce latency to 7 milliseconds, at least from rotating, change in head position until the moment the display responded. And the way they did this was they built a frameless ray tracer into an FPGA, and then they would sample head position at the very last minute after the frame had already been built and warp it. Most of the latency that resulted came from the actual scan from the display, right? So they were using a standard progressive scan, raster scan display, and on average, that introduced a certain amount of latency. And this is our work. I was talking to a couple of y'all earlier about this. So here we built a very simple prototype. This is a 64 by 64 LED panel. These are the tiles that are used in those virtual production walls that I showed you before. And we're driving it in a very unconventional way. So over here on the left, we're showing two of these panels, one driven in the normal way, one driven in our new way. And it's just looping here, displaying one frame again and again. And here we're grabbing frames out of that loop. So here you can see they're both blank. Then ours begins to fill in, and it fills in completely before the frame system even responds. And the result is we're able to get less than 2 milliseconds of delay from the moment the user presses the input device until there's a response. And if you're curious what this actually looks like, this is a Pong. So I mentioned this is frameless. If you look closely, you can see a little bit of sort of something like blurring as the ball is moving quickly back and forth between the paddles. And this is recent work at SIGGRAPH by, here we go again, Dwing Garajov and colleagues from NYU at 2022. And so they did some of this informative rendering work. What they found was that as enemies, the contrast of enemies was increased, right? So here's a low contrast enemy and a high contrast enemy. People were able to saccade to that enemy, essentially to attend to them and find them and respond to them more quickly than they were when it was a low contrast. That's just one facet, but this is experimental justification for some of the earlier techniques I was mentioning, like digital vibrance. So I think this is, I've been talking all about game rendering and where do we go beside photorealism from here. but I think it's about much more than game rendering. Obviously, for longer term, for augmented and virtual reality, where latency or delay is a huge piece or a huge chunk of the cause for simulator sickness or nausea, it'll be really important. So low latency rendering will be important. This is from an experiment at Microsoft Research more than 10 years ago now on touch devices. And here you can see, even with just 10 milliseconds of lag, you can see the cursor sort of wobbling beneath the finger. And it's not until you get down to 1 millisecond that it really seems to mostly stick to the user's finger. So low latency response here probably look different from 3D, but has big implications for the potentially billions of touch devices. And then even just a humble mouse, we often lose our cursors as we sweep them across displays, especially as they grow larger. And the lag in them, even if we don't lose them, can be annoying. So it also will have meaning for very traditional window displays. And to wrap up, what I'll point out is that so interactive computer graphics has been designed around the foundation that is over a century old, right? So over 100 years ago now, the way we started making motion pictures was by taking a series of individual frames and displaying them one after the other very quickly. As we became interactive, we based each of those frames on input. That was very natural. But now that there's a growing demand for even more rapid response to player and user interaction, it might be time to think about fundamentally different ways of making pictures, making real-time computer graphics. And if we do, like I say, I think we can become more of a leader in computer graphics as opposed to just taking what we can from film and television for recorded media. So with that, I'll invite you to come see two events I'm part of organizing. First is with Joseph, the Price Workshop, which is an esports technology and interaction workshop on Thursday at SIGGRAPH. Some of the work I presented here, or mentioned really here, will be presented in much more detail there. And you'll meet like-minded people. And then if you're interested in that demo that I showed with less than 2 milliseconds of latency, you can come see it yourself, play some Pong, play some Tetris, fiddle around with a mouse. Even you can see a higher resolution, not quite so low latency simulation of the same thing at Emerging Technology from starting Monday through Thursday. And with that, I'll stop and ask for any questions you all may have. Hi, Kurt.
Hey, I loved your talk, and I just wanted to say that, in a way, what your informative rendering discussion is the Silicon Graphics business plan. For we called it time to insight, right? But
yeah.
I spent a career targeting time to insight and not photorealism. I remember being really fascinated when HP many years ago got and said, well, we're doing workstations for photorealism. I said, yeah, and we're not. Right? That's because we care about people learning and getting insight.
That's right.
I'm glad you got to the history parts, because there's a huge history.
There is.
Of caring about
there's more that I didn't have time for.
Caring about latency at all. I wanted to mention also, the early ENS picture systems were calligraphic systems, which are a perfect example. They're frameless. The term, here's a little piece of history, the term display list in OpenGL, it's a misnomer, right? It comes from those calligraphic systems. They had a list of lines, And the way the machine worked is it ran through the list and drew the lines. Calligraphics, not a raster display, it just drew them. And when it got done with the list, it started again at the beginning. So the frame time, if you will, was determined by the length of the display list.
Nice.
Okay, so that's how graphics actually started, is without any frames. And then the frames were introduced later on. There's a UNC paper about frameless rendering, or
yes.
Is harmful, right? Which
That's right.
I get a little bit wrong, but the point is people have been struggling with this
Yeah.
for years and years. So I'll stop, but it'd be fun to catch up afterward. Thanks for your presentation.
Thanks, Kurt.
Thank you for the very nice talk. There's a lot of technology now in game pipelines that actually increases rendering, although the parent display frame rate is higher, so kind of super resolution, spatial temporal super resolution usually introduces additional latency. So my question is, how much do you think could predictive rendering solve here? Maybe try to bring the latency down to near zero. So what is your take on trying to predict the next few milliseconds?
Yeah.
Predictive rendering?
Well, there's a lot of technology. NVIDIA produces a lot of it, and AMD as well, that tries to do something very predictive or quasi-predictive. I've always been, and there's plenty of it, I've always been a little bit skeptical of that because it might make a mistake when it predicts. I'll give you one piece of feedback that we got from our demo on that little display I showed, where somebody was playing around with a mouse on that system. And they said, how are you predicting the mouse position? And I said, we're not predicting. It's just low latency. Yeah, so ideally, I think, the system should just respond quicker. That's my goal. I think you can make up for some latency with prediction, but every now and then you'll just go wrong also. Yeah.
Hey Benjamin, very interesting talk. I'm interested in your thoughts on that not all gamers are made equal, right?
Yeah,
so
sure.
Certain gamers would prefer the immersive experience over latency.
Yes.
Right. So they would actually argue against reducing latency but increasing realism. What is your thought on
Well,
that?
I totally agree that there's a spectrum, right? Even in very performative games where rapid response determines outcomes, there are segments where that's not nearly as true, right? And so switching back and forth between increased visual detail at the price of latency versus low latency at the price of less detail makes sense, right? And I think some players enjoy what I might call experiential games as opposed to performative games. Some of them will enjoy experiential games more than those performative games. So I think there's definitely a spectrum. The one thing I will add is that I think there is a limit, right? Like at some point, adding more and more realism, as we've traditionally called it, photorealism. I prefer spatial realism because that's what we're really doing is making color change across space more accurate, right? At some point, that becomes unsustainable, right? And many players across many titles are experiencing that. So, yeah.
So I just want to stick in a plug here for availability.
Availability.
Of the game to the game, where we could use the same technology instead of moving photorealism or spatial realism or even temporal realism, give people access to the current level of realism in a form factor that they have on their person already, potentially.
Yes.
And so that's that could increase the ubiquity, the market size. The margins are going to be smaller, but it could grow the business, I think.
Yes, I think that we already have some of that. So that chart I showed with all the spark lines, the squiggly lines, and where I pointed to the 80% at the top, that was a study of how Dota 2 players configured their game settings. So they were doing what you're describing. They were trading off visual accuracy, or at least additional visual detail, against more or less latency.
Well, but what I'm saying is that that also lets you say, hey, let's not require as much of a hardware device to be able to play this game. Give me something like a Steam Deck or a cell phone that can now deliver the experience of the photorealism of a 10-year-old game, but today and now when I'm on the bus or in the checkout line, instead of having to go someplace and play.
Agreed. Yeah, so even in the game industry, most of the gaming market is on phones, right? And so you can't play the same kind of, given a title like a AAA title, it won't look the same on the phone. So like you're saying, if you want to make the same title accessible across all these ranges of devices, having these kinds of controls, or at least the ability to change the rendering demand, could be important. In fact, when I talked to this about this with some certain people from the mobile industry, they got excited about power in particular.
Thank you.
Hey, Joseph.
As long as we're talking about the market, you mentioned mobile being a big part of the gaming market, but a huge percentage of this is games like Monopoly Go, which are very different in their interactivity than what you've been advocating here.
Yeah.
So I guess I'm wondering, what are your thoughts about the size of the market, or the percentage of the market that is this very interactive, high interactivity, time to understanding or whatever, versus the ones that are way more casual, or even pure video based, right?
Yeah.
Film is not interactive.
Right. Like I used to play this game. I'm pretty old now, so I used to play this game called Myst, which was just a series of stills. I don't even think there were video in that. But yeah, there are ranges of games, different types of games. Definitely some games, some applications much more demanding in their interaction than others. I will add, though, that mobile devices, like we saw, can be annoying in certain uses when even there's just a little bit of latency, right? So, for example, I just have given up signing my name at the cash register. I don't know about y'all. Even on my phone, it's not good enough. So we could do better. And so sometimes just the interface demands lower latency, because the touch in particular interface is particularly demanding because it unifies the input mechanism, your finger, into the same space as the output mechanism. So you can explicitly see the mismatch between where your finger actually is and where the device thinks your finger, or at least is telling you your finger is, right? And similarly, it's similar with augmented reality. There's a real world view, and we're trying to overlay virtual things on it. The real world has no latency, like it's completely up to date. Your device is lagging behind, right? So those are very demanding settings. So even a mobile device can, even on some fairly mundane applications, be pretty demanding.
In terms of latency...
Oh, there you are. Okay.
Yeah. So latency is impacted by a lot of factors which are outside our control, like the OS itself, the hardware device, whatever driver it's running, whatever driver the GPU is running. So there's not a lot that, as an application developer, I can control over latency. So what are your thoughts on, apart from VR, AR, what can drive the reduction in latency in that front?
Oh, you mean you as a user or you as a researcher?
As a researcher.
Oh, as a researcher. Okay. Well, as evidence that people care about this, at least in gaming, there are, and Joseph is intimately familiar with these, mice that lower latency. So there are new kinds of mice that have been designed and are being sold to lower latency. Same with displays, right? The basic mechanism right now is just very high refresh rates, sort of approaching ridiculously high at this point, right? 500 hertz. I went to SID this year, there was a 1,000 hertz refresh. So you can do that. That will help. But both of those, we're sort of reaching the point of diminishing returns. Most of the delay at this point, especially if you have some of those devices, is in the CPU, the GPU, and the way in which they all communicate, right? And I think Joseph was part of designing NVIDIA's Reflex package, which optimizes how input reaches, goes from the input reaches the CPU and then is passed on to the GPU. That will lower latency. If you don't care very much about tearing, you can reduce latency some more by turning off vertical sync. But as a researcher, after a point, you have to try to figure out something else. So we're not using yet GPUs. We're using Raspberry Pis and FPGAs to prototype what we want to do, different kinds of pipelines to produce our images. And I'm not the first to advocate for rethinking the way we make images with new kinds of hardware like FPGAs. FPGAs are, in fact, designed for prototyping new kinds of computer hardware. So I would get into it if you're serious. It's fun. It's nice to have a lab that's full of wires and stray screws.
Nice talk. Earlier, you had mentioned that reducing the visual quality helped improve the latency, and that some of the gamers were going for that. Back in my younger days, when I played Twitch games online, I went to like negative bitmap levels, but not so much for reducing the latency, though that's part of it, but to reduce visual clutter.
Yes.
And so I was wondering if you kind of explored that a little bit.
I haven't personally. A couple years ago, we ran a Frontiers workshop at SIGGRAPH, and one of our co-organizers, I think, or at least co-presenters, Byung-Ju Lee, presented some research about exactly this, where they measured visual clutter using a at this point, fairly standard psychophysical measure, like scientific psychology, visual psychology measure of visual complexity and clutter, and found that, yes, if you turn down the settings on that game, I forget which game it was. Do you remember, Joseph? No. If you turn down the visual settings in that game, visual clutter measures declined. They didn't carry it forward into performance, but at least they carried it that far. So you have both evidence on the in practical side, players are doing this because they feel like they perform better, and then some approaching evidence from the scientific side as well. Sorry?
I think that goes with visual salience.
Yes. Yeah, so there's visual clutter, which is just the overall complexity of the image. And then there's salience, like the same complexity with more visually obvious or more visible edges or textures.
So one of the things that occurs to me when we talk about latency is that not all things really need the same level of like latency. Like you don't have to hit the same latency targets. So like things like VR, we know that we need really low latency for head tracking, otherwise you induce motion sickness. But do you have any like idea of what the things that need like really low latency versus like things that don't really need as low of latency, like maybe updating the light field or something like that?
So I can start a list. Trying to generalize might be difficult, but yeah, you mentioned AR, VR. I think AR even more than VR because there's a visual mismatch. Like I was mentioning earlier, you can see it in the same visual space both times, right? Either end of the latency. I was mentioning touch displays, same sort of thing. Any place where the input and the output are in the same space. Games that are just more demanding of rapid response, particularly games where two opponents are trying to act on one another, so the first mover is often the winner, right? I have become fascinated by sim racing. Does everybody know what sim racing is? Okay, so if you're into, my son got into Formula One, right? Then Formula One has been around for decades. They were training in more traditional ways, but then recently the pandemic happened. Nobody could race anymore. So many of the top F1 drivers started using software, PC-based simulators to keep their skills up. And then those became integrated into their actual training regimen after the pandemic. And those are extremely demanding, right? So they're sort of the ultimate version of, where you have almost unlimited budget to make an immersive kind of virtual reality simulator of a real thing. So they have to integrate platform motion, haptic response on the steering wheel, vibration in the chassis, and of course visuals and sound. All of that has to be integrated, and all of them, they want to have latency under 10 milliseconds. And in some cases they are achieving that, not in all the modalities. I'm probably leaving some more out, but that's a good start, I guess. As to what's less sensitive, things like turn-based games, probably not a big deal. Can you think of others, Joseph? Okay. Mark Claypool is one of our colleagues whom we often collaborate with, and in fact, he'll be presenting the keynote at the, what's the price, remind me, what a price stands for? Performance, Rendering, and Interaction in Competitive Esports. So Mark Claypool will be giving the keynote at that workshop on Thursday if you want to see what his thoughts are.
Okay, I guess we have to end this now. Thanks.
Sure.
Ben?
Thanks, everybody. I enjoyed it.
We will now be moving on to the last paper session of HPG, but before we get to that, I have a quick announcement, which is that we are going to have a vote for the best paper of HPG 2026. So Joris and Rikard will be walking around here during the paper session to distribute these paper ballots. And up here you get to enter some numbers to vote for the 3 papers of HPG that you liked the best. And then right after this paper session, we will be collecting these paper ballots and we'll be counting them. And then a little bit later, after the break, during the awards and closing session, we will be announcing the winners, not just of the best paper award, but also of the student competition So yeah, please make sure that you get one of these paper ballots. We will also be handing out pens, and then please make your pick. Yeah, and with that, we are ready to get started with the paper session. So, yeah.
All right. Welcome to paper session 5, physics-based simulation. Our first presenter will be Yu Yang, and he'll be presenting periodic Anderson acceleration for GPU-based elastic body simulation.
And wait. Okay. So I think I should use this. Yeah.
Yes, it's USB-C, and there's going to be some.
Which is the HDMI cable.
Probably this
one.
So.
Yeah. So
Yu Yang is the PhD student at the University of Houston, and he's working on real-time physics simulation for deformable bodies and 3D agents in VR environment.
Oh, sorry. Okay.
So if it's showing up here,
Is that what you ready?
Yeah.
Oh.
Wait. There's some. There's Okay. Hi everyone. I'm going to talk about how to make local and GPU parallel solvers for elastic bodies converge better and without losing their performance. And so first, what's the application of the soft body simulation? So it can be used in games and virtual surgical training. So some medical teams, they train their doctors with virtual surgery system in VR environments. So and the soft body simulation can provide the doctors with realistic experience for surgery and also content creation. And first, I'm gonna introduce what are we gonna try to solve for a physical simulator. So basically, at each frame, we take a time step size and we calculate an global energy, so which contains the inertia and also elasticity terms. And inertia it's just want to keep the momentum and move with the gravity. And the elasticity wants to preserve the object's shape and volume by elastic energy. And so the solver is try to minimize this global energy at a time. And so take this as an example. So this is a tetrahedra, and initially it has 0 elastic energy, and if you stretch that, it will has some elastic energy. And after the solver, after some iterations, elastic energy goes down, and it tries to go back to its original shape. And nowadays there are 3 families of solvers. One is global solvers, which solves all vertices at one time. So it's take a very big step, but although it converges in few iterations, but each iteration will take a very long time. So it tries to solve one big problem at one step. And the second is local solvers, which focus on tiny problems. So where it tries to move each vertex according to its adjacent vertices. So the problems are solved locally, and it can be parallelized, but and it's also cheaper, but it may not converge as well as the global solvers. And recently there are some combined solvers, so we try to combine the 2 kinds, so like a multi-grid, and so it tries to maintain something like a min-map or a level of detail thing. So it tries to preserve, reduce global errors by some coarse design, and also focus on solving local problems by refinement steps. And so we observe that local solvers, they are well suited for GPU for parallelization, and their only weakness is that sometimes they may cause big global errors. But could we add some corrections, add some global coupling to a local solver, and so it can reduce the global error, and just with a little extra things. And so we choose VBD, vertex block descent, as our baseline because it's one of the latest work of the local solver. And so you don't have to exactly understand how it works, so you just need to know that it's a local solver, and it can guarantee the global descent unconditionally. So that's why we choose that, because without that condition, if you parallelize a local solver, it may not converge. So this is the unconditionally guarantee of convergence is one of the reasons we choose VVD. And but it's still local solver, so it still has the drawbacks of the local solver, and we try to improve on that. In the original paper, it's already built with an accelerator with this, which is Chebyshev acceleration. So basically, it maintains the momentum of each vertex. So it can help the VVD to converge better. Yeah, but we think, but it's still focused on the local problems. So this mechanism still doesn't help solving the global errors. And so basically, each VVD sweep is just a fixed point iteration, and so the bottleneck is the locality of this function, and so what is Anderson acceleration? So it's something like the root finding method by extrapolation. So like, in this graph, I mean, if we know two previous states, which is x0 and x1, and we assume the system, I mean, it's near linear within a range. We assume it's near linear locally. So in that case, we can extrapolate to try to guess a route where the error is 0. So, and this is one example. So Anderson acceleration is just the same idea for the x in millions of dimensions. And in Anderson acceleration, we can choose how many history states we use for extrapolation. So here we set it as m+1. And as previous paper already proposed, and Anderson acceleration is a multi-secant quasi-Newton method, and it extracts global information from local sweeps. So the way we did that is we save some history states when the solver iterates, and then we use that to try to extrapolate a state that can lower the global errors. And but why we just don't use Anderson acceleration instead of Chebyshev? So the problem is, first thing is, they cannot run in the same step. So because they are both some kinds of extrapolation, so they cannot run in the same step, but they can run in separate steps. And if we only use Anderson acceleration to replace Chebyshev acceleration, the problem is it introduces a very high overhead. So although it helps the solver to converge better, but the overhead just makes it not practical for real time. So, and our method is we run Anderson acceleration periodically, so it's every few steps. And by experiments, we choose a k equals 16, which is the gap between two Anderson steps, as the between the Chebyshev steps. So basically, and Chebyshev can help the local convergence, and our method, so introducing periodic Anderson acceleration, helps correct the global error. So in the experiment, well, we also find out that if we use a larger M, it may not help convergence and it introduce and it's more expensive. So we just use M equals 2 for our results. And the algorithm is simple like this. So we just replace some Chebyshev step with Anderson step in the original VVD algorithm. And here is one result. So here we use tetrahedral meshes for elastic body instead of triangle meshes, and we run our experiment on a single RTX 4090, and we observe the elastic energy. Basically, if it decreases faster, it means it converges better. And this is a beam. So this is the side view of a 3D beam. So it's 3D, just a side view, and its left side is attached to the wall, and the right side will fall free. And so, no, sorry, maybe, wait. Let me see if it's, okay. So you can see in the left side, I mean the green one is VVD and the Chebyshev, and the black one, the black one is Newton as a reference, using Newton method. So our method is closer to the Newton reference than the original VVD and the Chebyshev. Okay. And we tested our method on this case on various resolution and stiffness, and you can compare the blue one with the green one. So in these cases, our method always retrieve a lower elastic energy. And this is another demo. So we pull the nose of this object suddenly to far away, and our method, you can observe it pulls the upper body, earlier than the VVD method, because it can, try to capture that trend that it tries to pull the upper body. So this is, why we can reduce the global errors. Yeah, and this is the plot of the energy curve, and we achieve lower energy both in the same iteration and also in the same running time. And we did some ablation of K and M. So here we got M equals 2, 3, 4, and K from 1 to 40. And we found that if we fire Anderson step very frequently, so the average step will be much higher than the Chebyshev reference. And so just by this ablation study, we chose M equals 2 and K equals 16 by default. And this is another example where an object is flattened and it tries to bound up and to resume its shape. Yeah, so basically you can see in the second and third row, the second is Chebyshev, and the third row is ours. So in the, in the same step and our method, it resumes the shape, original shape, more quickly. And this is the energy graph of this thing. We measured the performance on those things with various resolution of mesh, and we found the overhead is at nearly 0 to 10% approximately, and it can reduce the it can achieve 6% to 49% lower elastic energy with this overhead. And the limitations is, first, it does not guarantee the descent of energy, because sometimes extrapolate, you can get it right. You can get the right route in one step. So it's just an approximation. So sometimes it can be worse than not using it. And the correction is low rank and just an approximation. And also, our method is not suitable for collisions, because in that case, the the error is likely to occur when on the contact area, so which is high frequency and spatially localized. So local solvers are, they are designed for reducing that error, so they can do better. In that case, but the Anderson step won't help in that case, where the local high frequency errors is high. And also, the optimal K for each problem is also, it's also problem dependent, but we just find a default K that suits most of the things. But actually, if you want a better K, you still have to tune it for each problem. And so what's this contribution is, it can do the global coupling without creating a global object like those combined methods do. And also, we show that the two accelerators can compose rather than compete. And the right question is to ask for real-time performance is the convergence per millisecond. Yeah, and so this is my work. So thanks for listening. Any questions?
All right, very nice talk. Thanks so much. Any questions? I can start with a question. So say, for people who already have a BBD solver implemented, how easy it is to integrate your solution?
Sorry?
If you have if there is an existing solver, how easy is it to integrate your approach into it?
Yeah, so if you already have a solver, so you just record the state every few steps. So like I said, K equals 16. So you record the vertex positions every 16 steps, and you run Anderson acceleration. So I mean everything 16 steps. So it's just use the Anderson acceleration step to replace the original, I mean, iteration every few steps. So yeah, it's simple.
All right. Then maybe another question. You mentioned the parameter values, right? You say have a k equals 16, m equals 2. Does that work pretty good on average? Is that a good starting point? How universal are those tuned parameters? Would those work for pretty much for every scenario, or you need frequent retuning?
I mean, because actually, I mean, maybe we need more experience because we just tested our method on the the three things I just showed, but it already includes like the extreme stretch and also the some smoother and some like not too extreme stretch. So, but if we need to justify the how general is that parameter, so maybe we need more experiments and more results.
Yeah. Yep, makes sense. Also, so the examples you presented, right? They mostly use constant stiffness, right? It's the same stiffness throughout the object. Have you experimented with any variable stiffness examples, like if one part of armadillo is soft, the other part is stiff?
Well, not yet, but yeah, we will consider it in the future work.
Okay, sounds good.
All right, thank you.
All right, let's thank the speaker. All right, our next presenter will be Tim McGraw. The paper is Real-Time Dissectable Deformable Models Using High-Performance Breakable Shape Constraints.
Do you know how to drive this? Yeah. No,
Tim's associate professor in the Department of Applied and Creative Computing at Purdue University. And he previously worked as the game developer at Rainbow Studios, Electronic Arts, Tiburon, and Shell Games.
Great. Thanks for the introduction. Thanks to Michael Doggett for letting me use your laptop. Thanks to everyone for sticking around for the last paper. I'm Tim McGraw. Jack Myers is my MS advisee at Purdue University. He's over being a student volunteer now, so definitely say hi if you see him. The goal of our project is to develop deformable and dissectable models specifically for anatomy education applications. Existing commercial applications like Anatomage and Sectra have nice volume renderers, and they allow you to interact with data sets using clip planes and tissue transparency and rigidly transformed segmented meshes. We haven't found any existing systems for anatomy education with interactive, deformable, and fracturable models. And our hypothesis is that a more engaging and physically grounded system will lead to better learning outcomes compared to those other virtual systems. This is just an initial prototype we describe here. We have not really assessed that yet, but that is part of our future work. The source data for many anatomy education tools and for our models are cryosections, which are color images of frozen cadavers. The Visible Human Project is one of the most famous cryosection projects. In the mid-90s, researchers at the University of Colorado, funded by the NIH, acquired high-resolution male and female whole-body image stacks. Susan Potter was the anatomical donor for the Visible Human Female, and in this image, you see the acquisition of one slice of that data set. This is what the raw data looks like as we get it. You can see the cross-section of the blue gel, color correction cards, numbered Post-it notes for each slice, and we want to, with as little manual intervention as possible, create our models from images like this. Here are the three-letter acronyms for some of the deformation and fracture approaches that are mentioned in our literature review. Finite elements have a long history. They give you engineering accuracy, but at the cost of performance. As you can see in the image, it's capable of representing very fine details of fracture. Material point methods have been a visual effects industry darling. The snow from Disney's Frozen, for example, was made with MPM, and performance still outside of the interactive realm for many applications. PBD is a technique more suited to interactive applications like games due to its stability and easily parallelizable local solver. By creating constraints between particles, we can construct rods, cloths, solids, and other deformable structures. Shape matching constraints are a non-physical approach. They find the least squares mapping from the rest pose to the deformed pose of a model. And lattice shape matching, as shown in the image, uses a system of overlapping shape constraints to find a locally linear transformation that represents deformation. So our models use PBD and a grid of shape matching constraints and some new approaches to breaking those constraints. Our input data are the image stacks that we talked about, so defining our model on a grid is natural, and the regularity gives us several benefits. One being that we can easily partition our model into only 8 partitions without solving a graph coloring problem. An issue with PBD reported in the literature and observed in even the previous talk was slow convergence due to the local solver. In a chain of constraints like the one shown on the right, constraint violations tend to propagate through the system one sub-step at a time, which can make the system appear more flexible than desired. This can be overcome by increasing the number of sub-steps per frame or by adding constraints over larger neighborhoods. Our approach is to keep track of evolving connected components as the model fractures and add a shape constraint over each connected component. We compute a union find structure over the model graph and update connected components every frame. And by changing the weight on this constraint, we can control apparent stiffness. We also avoid a lot of bookkeeping headaches by not embedding a triangle mesh in our model, but instead embedding splats. We keep a per splat sign distance to the surface for fast culling and easy implementation of some dissection interactions using Boolean operations. We also avoid expensive computations like eigenvalues for principal stretch and use cheap proxies like the least squares residual from shape matching as a fracture criterion. So there's really, despite the name of the session, very little actual simulation or physics being done here. To construct our model over a desired region of interest, we first crop the images and alpha mat them. We use InspireNet for the foreground-background segmentation. And thanks to the specimen being frozen in that blue gel, we can get rid of most of the remaining blue areas you see, for example, in the sinuses here, with just color keying. We then overlay a low-resolution particle grid over the foreground and compute the sign distance to the interface. Our lattice of shape constraints is defined over 4x4x4 regions of particles. 64 particles in 3D is a multiple of common GPU subgroup sizes, which is no coincidence. Likewise, we embed 64 splats into the cells between regions, or between particles. The stride between adjacent regions is 2 particles in each direction, so each particle can belong to up to 8 regions. Here's what the model looks like starting at the particle level. These particles are also our collision primitives. We found a good level of model flexibility with a 32 by 32 by 32 particle grid. On the right is our splat resolution, which might seem low, and it is, but we're going to interpolate at render time, which is also easy because everything lies on a grid. Here's what one partition of splats looks like. For some operations like level set redistancing, we dispatch shaders one partition at a time to avoid read-write conflicts. After interpolating splats by a factor of 2 by 2 by 2 and texturing them, we get a model that looks like the right-hand image. Some data sets, like the Korean visible human, are segmented into non-overlapping tissue classes. In this case, we also store a tissue class ID and sign distance to the tissue class interface in each splat. We use this later to support excision of anatomical structures. At each substep, a compute shader computes the per region shape constraints and contributes to the per connected component shape constraints. This shader is mostly a sum reduction. Per particle, we compute the goal position in terms of region and connected component transforms, denoted by Fs here. The final particle position is a lerp between the current particle position and the goal position. The W sub ij values are based on the distance of particle I to the centroid of region J in the rest pose. The parameter of the lerp and W sub ik give us control over apparent stiffness. This is a demonstration of the level of flexibility we get from our overlapping constraints. We also demonstrate a scrolling rest pose clip plane during this interaction to show the internal details of the data set. Dissection operations happen outside the compute and render loop in response to user interactions. Progressive here means continuously computed by frame by frame. Cutting is not progressive. It's only computed in a single dispatch after the mouse button is released. Tearing, on the other hand, is progressive. Shattering in this context, pardon me, is the tendency for many particles to simultaneously exceed the fracture threshold, causing the model to suddenly break into many pieces. This is something we work to avoid since it looks unnatural for soft tissues. And excision is the ability to grab and remove segmented anatomical structures. In cutting, the user sketches a piecewise linear cut path with the mouse, which is extruded to form a 3D cut surface. Cut regions are duplicated. Then the splats in regions A are intersected with the cut surface psi, and the splats in regions B are intersected with the negative of psi. We replace some particles, shown in white, with ghost particles in a narrow band around the cut. So the ghost particles serve two purposes. First, the shape constraint is under-constrained if a transformation from the rest pose to the deformed pose can't be uniquely determined. In that case, the covariance matrix of particle positions can't be inverted. Adding ghost particles helps prevent this problem. Second, in our model, we index splats relative to the indices of the particles, so we can't have splats in a cell unless we also have the particle that defines that cell. And this is what cutting looks like on the final rendered model. We also show a debug view showing distance to the cut. We implement tearing without region duplication. We simply remove particles from regions unless the particle belongs to only one region. When a particle is removed from a region, some splats are also removed based on a splitting plane that separates the regions. We minimize shattering and encourage progressive tearing by forming a partial one-to-one mapping between torn particles and regions. This minimizes the number of torn particles per dispatch, which allows shape constraints time to relax and avoids the shattering problem. And this video shows the progressive nature of the tearing interaction. We consider tearing a secondary interaction that will be used mainly when cuts don't go all the way through the model and the user wants to access the cut surface. Excision uses region duplication like cutting does. The excised class, shown as red splats here, is subtracted from A and unioned with B. As a result, B is a homogeneous region containing only a single tissue class. Pardon me. We use the tissue class SDF when excising to initialize the SDF for the splats in regions B, and also to initialize the SDF of the whole left in regions A. And here's what excision looks like in action as the eyes and then the cerebellum are removed. To render, we dispatch one task shader workgroup per region. We deduplicate cells because regions overlap. This overlap means splats may belong to 8 different cells. We also do culling and interpolated splat amplification at this stage. The maximum number of interpolated volumetric splats without culling would be 16 million. Each mesh shader workgroup processes 4 splats, so may output 32 interpolated splats, which is 128 vertices. We compute interpolated per splat transformations here, as well as other properties we need for rendering. Splats are then projected to the SDF equals 0 isosurface and are aligned with the SDF gradient. Splats are textured with the cryosection 3D texture in the fragment shader. These splats aren't blended like Gaussian splats. We use coverage to alpha for a clean splat cutout. These are our times compared to MPM and FEM. The capital N's are counts of regions, particles, and splats after culling. MPM and FEM times do not include rendering, so compare them to the far right yellow column, which is the sum of region and particle compute times. Render times here, while still not great, were updated after recent optimization, so they don't match what is in the paper. Freeform cuts and intersecting cuts are handled easily. Intersecting cuts are something not naturally handled by some techniques like XFEM. Here's the performance of our tearing shader. The left plot is compute times. Spikes over 9 tearing operations are spread out in the region plot due to the redistancing shader that runs after tearing to restore the sign distance property of the splats. Render times on the right increase as the surface area of the model increases and more splats become visible. Here are some more excision results. Even though we see good visual detail most of the time, structures approaching the uninterpolated splat size, like the Digimouse ribs on the left, can't be well represented. Here we demonstrate variable material stiffness from the segmentation by excising and shaking some structures. Without haptics, the visual reaction to applied displacements is what gives users an impression of what the tissue mechanical properties are. The spinal cord and corpus callosum react like soft tissues, and the vertebrae and bones of the skull are rigid due to their connected component constraint weights being higher. This is the performance of the excision shaders. We excised 3 structures from Digimouse, starting with the liver. Being a large organ, it resulted in a large increase in the number of visible splats and corresponding increase in render time. Excising other smaller structures resulted in a more moderate increase in render time. Our conclusions: the low-res physics seems sufficient for this application. It doesn't prevent us from getting a native resolution visualization of the cryosection data. However, low splat resolution can result in artifacts on small or thin segmented structures. The dissection operations support exploration of the cryosection image stacks at various scales and permit the user to resolve visual occlusions. But we want to get the system in front of educators and students and see how they use it and what features make the most sense to work on next. The bottom point, image generation is a big one because of the quality issues in available data sets, like missing slices, misaligned slices, and segmentation errors. And B, because we don't have permission to redistribute the data sets except for the visible human, but those aren't segmented and we lose a lot of important functionality without that. So that's all for the talk. I'll take any questions now. Come see our live demo at that other conference down the street on Tuesday night.
Thanks. Great talk. These are really fun visuals. I was wondering, when you cited those render time speeds, what kind of hardware are you running this on?
That was a 4070 laptop.
Laptop. Okay. Okay. So these are laptop times and performances.
Yeah.
And does it? And I saw you said that you were looking at like optimizing for VR. Like as of right now, what does that look like? As in, like, I assume you guys probably tried it and.
No, I haven't actually haven't tried it yet. But yeah, we definitely want to get multiple milliseconds lower per frame there.
Cool. Thanks.
Yeah. Thank you.
Super interesting talk. So I was wondering about the cryosection data. Could you actually extract, let's say, fluid properties out of this data and incorporate it in your physics simulations?
So just based on color, it's pretty difficult. You know, if you look at the cryosection data, let me go back to some of the raw data here. You kind of imagine bone as being white, but you're usually looking at like bleached bones. But as you look at like the skull and the cross section here, by color, it's really very similar to some skin tones and some other tissues in the brain there. So just based on color, it's pretty difficult. If you were able to register with CT or MRI, you would have some better luck, but usually those are going to be a different resolution from the cryosections. So it's difficult. So that's why our goal moving forward with data is to do generation and generate segmentations and then synthesize cryosections from segmentations. Basically go the opposite direction.
So given enough data, could you learn these properties from the data, essentially?
If I'd say if I had perfectly aligned, very high resolution CT, so our physics in air quotes is really very approximate. Our physical properties exist at the particle resolution because that's where the animation happens. So per splat, physical properties don't do anything for us. And so already it's so approximated. At this point, really, we just identify, is it bone or is it not bone? We really just have two sets of mechanical properties. Again, mechanical in air quotes there.
Cool. I just want to continue on with that question. So does your system support multiple data sets that combine together? Because, for example, the Allen Institute has a very high resolution, not very high, but they have a segmented human brain.
Mm-hmm.
Can you add that to your model, and now you have a segmented human brain as part of your model?
If you're able to perfectly register those, you could, or you know, I suppose you could also just visualize, if you had MR data and the segmentation of it, you could just visualize and dissect the MR.
Okay.
But yeah, we could pull in really any type of rasterized data, well, even the voxelized mesh, right? We could pull it in the armadillo. So sort of any data on a voxel grid, I think we could do something with. But yeah, I think our best bet moving forward for the best results is things are high resolution, perfectly aligned, and I think the best way to do that is synthesis and generation. There's just so, I could say yes to that, but the thing is you get these data sets and you find, missing slices, you find misaligned slices, you find noise, you find motion artifacts and things like that. The freezing process on cryo sections changes the appearance. So there's so many issues with the real data sets that I hesitate to say, what you could really do with a real data set until we get our hands on it and really inspect it.
Cool, thanks.
I'll ask a question. Okay. You mentioned volume preservation as your future work.
Yeah.
Do you have any thoughts on how you may approach that?
I guess we were thinking slang auto diff maybe to get the volume preservation. That's one thought. I guess another thought is maybe it's not that important. So yeah, I think it's maybe one of those on the future wish list down the road. If anyone has any ideas on the volume preservation, let me. So, and what we would want is local volume preservation, not the global. So there's some approaches with to do the global volume preservation. We really want like sort of locally, you squish it here and it bulges there, sort of nearby, and maybe making that localized. And I think maybe incorporating that with the hard tissue like bone would be difficult, right? Because you don't want to squish the brain and have the skull bulge, for example. So it could be tricky. Could be tricky to get that working.
Yeah, makes sense.
Yeah.
I'll maybe ask another question. I thought the texture splatting looked really impressive. That really made it detailed. I did notice that when you do a cut, especially not when it's axis aligned, when it's kind of cuts across a little bit, you see the voxelized structure a little bit. Maybe more noticeable. I kind of really zoomed in on those pictures in the paper. And I was wondering if you have any thoughts on maybe smoothing it out and maybe introducing some kind of cut cells.
Yeah. So are you talking about sort of at the top here?
Yep.
So we have some. So as you look at sort of the way the model is laid out here, the splats in a cell kind of belong to the particle at its lower left, and so there's sort of a shifting artifact here. So that sort of, I think if we were able to sort of structure it so the splats were centered on the cell that they belong to, it would fix some artifacts, but there may just be sort of a cheap workaround for that problem. But I think probably the sort of more principled approach would be to look at sort of shifting, having one grid shifted relative to the other so things are sort of a little more centered, because yeah, we do sort of get a bias there just due to the way splats are organized.
Right. Thank you.
Yeah, thank you.
Well, let's thank the speaker.
Okay, and quick reminder and also info for the latecomers to this session. We are doing the best paper award right now. So if you haven't gotten one of these paper ballots yet, you can ask Joris or Ricard. And yeah, please make your pick and then give us the paper ballot. Thank you.
podcast short.
Looks good. You still on microphone? Here comes Christoph.
Hello, everyone. I'd like to get the closing started. So this one's a little bit hectic because we're creating material in real time. But our first thing to get into is the student competition. And Akshay is going to tell us about the entries, a little bit more detail about the different entries, and tell us about which ones he thought should win the prizes. Okay, so.
Thank you. Thank you so much. This is my first time at the committee meeting, the committee at HPG. I'm very excited. I'm very grateful to the committee itself. And we're nearing the end of this conference, but last but not least is student competition. The theme this year was vast proceduralism and global illumination. So a combination of creativity and performance. We had 5 entries this year, all ranging different types of proceduralism and different approximations of global illumination. The QR code that you see here will take you directly to the web page with the links to all these entries. All the entries were required to submit a shader toy implementation of this theme. We got submissions from all across the world. There was Infinite Cyberpunk City from University of Southern California, local here. Procedural Neon Metropolis Global Illumination from Huazhong University of Science and Technology. A Thunderstorm Terrain from the Indian Institute of Science. Artificial Lights from Vinicius University de Estual de Campinas. And Maya Saba from the University of Utah. Let me talk through what the ask was before announcing our winners. The concept behind it was to invoke creativity and ask them to work on procedural artifacts with unending vastness of the world. So 2 important parts of it was procedural techniques that enable the creation of large-scale worlds without manual modeling, and the second part of it was to be coupled with global illumination that reveal realistic lighting, shadows, color bleeding, and more physically accurate effects out of it. And so the third place winner was Infinite Cyberpunk City, a local Nan Lee from University of Southern California. This is a screenshot, a screen grab from the shader toy, and the QR code on the bottom here will take you directly to the shader toy link there. It was a great demonstration of vastness and proceduralism. The blocks here were generated procedurally, and there's cars moving around in the scope of the scene that also were illuminated and kind of implemented with next event estimation and a single buffer A pass with self-feedback and temporal accumulation. And so this is the third place winner for the student competition this year. I don't know if our student is here, so let's congratulate them virtually at least. Thank you. And the second place winner is Maya Sabha Hall of Illusions by Rishikesh Vidya, University of Utah. This, the student reports, is procedural SDF Palace Hall inspired from the stories of Mahabharata, a mythical Hall of Illusions. And the implementation here works on repeating chambers, arches, columns, and internal scene with proceduralism. And for the global illumination part, the shader uses progressive Monte Carlo path tracer with multi-bounce indirect lighting, next event estimation for emissive lights, and MIS weighting. The concept here is basically an internal exposition of never-ending lights, never-ending arches and scenes and interiors. And the work here demonstrates that very beautifully with interactive experience for global illumination. So this is second place winner Rishikesh Vidya. Not sure if they're here, but let's go ahead and congratulate them. And for the first place winner, drum roll please. First place is Procedural Neon Metropolis GI by Hao and Gao. This is an amazing implementation of a procedural city that works very interactively on your browser. I dare not open it up on my MacBook though. And it implements procedurally generated cells for roads, plazas, towers, podiums, glass needle towers, metal slabs, and multiple different patterns as you explore. And for the indirect lighting, the global illumination part of it, there's stochastic path tracing involved, reinforced by a deterministic procedural city. And there's an irradiance field derived from the same hash that generates the city here. And it's an excellent demonstration of both vastness and proceduralism combined with global illumination. And this is our winner for this year. So let's go ahead and congratulate them. The reports of these students and their work that they've done will be available online on the web page. Until then, please enjoy the shader toy work and implementation. And that's it for now. We have our winners, which I don't know why the numbering is kind of messed up, but this is number 1, Maya Sabha, and then Infinite Cyberpunk City. Thank you. And I think next up we have Christoph to talk about papers.
Thank you. So this award session will be slightly improvised because we have had enough time to count the ballots. We have our result. However, we were a bit tight on time to put it onto slides and to print the certificates, but the certificates will be created in the next few minutes. Nonetheless, I will now announce the winners of the Wolfgang Strasser Best Paper Award. And as usual, we will announce third place, second place, and then finally first place. And I'll need a little bit of help from all of you to, ramp up the excitement. So for the third place, we actually have something slightly unusual, which is we have a tie. 2 papers got the exact same number of points in our vote, so both of them win third place. So before I announce the first one of these 2 third place winners, please give me a little drum roll. So, third place goes to Ray Tracing Massive Amounts of Animated Geometry by Holger Grün, Carsten Bentin, Michael Kern, and David McAllister. Congratulations, and please come up to the stage. Congratulations, well deserved. Okay, and our other third place is, drumroll, Real-Time Path Tracing of Massive Dynamic Foliage by Dietger van Antwerpen, Pascal Gautran, Ed Bidulf, Christoph Kubisch, Jan Schmidt, and Martin Stich. Congratulations. Well deserved. Thanks. Okay, now moving on to second place. No tie here, so we have a single winner of the second place of this Best Paper Award. I need a drum roll. The second place goes to Memory Efficient Bounding Volume Hierarchies with Merged Nodes by Jakob Heidel, Cem Yüksel, Eric Brunyard, and Andrew Kensler. Congratulations. Congrats. Well deserved. Okay, and now for the winner of the Wolfgang Strasser Best Paper Award of High Performance Graphics 2026. Well, I need a drum roll. So, the winner of the first place is Compatibility Guided Neighbor Selection for Restia by Orion Jenkins, Markus Kettunen, Dachi Lin, Ravi Ravamorty, and Chris Wyman. Congratulations, great work. So yeah, as I said, we'll have the certificates ready in the coming minutes. You can collect them from us, so please stick around a little bit. And now I think Michael will say a few more things about this conference and HPG 2027. Thank you all for being here, and have fun at SIGGRAPH if you're going there.
Come on back. Come on up.
Okay.
One more thing.
Yes. Now the thing is, I also forgot to make a slide. Actually, do you want to do closing first and then I'll announce it?
Okay, so I don't have too much to say, but I do have something to say. So there's one award that the general chairs pick the sort of outstanding committee member. So this is a way to recognize how much effort committee members put in, but in particular, some put in a lot more that really helps us all out. And so Ingo and I had a very heated discussion about the many great contributions that everyone made this year, but we finally decided on Will Usher. So come up, Will. Will has done all the local organization with USC, so he's the one to thank for the food and everything, and he did a fantastic job. I mean, I'm in Sweden, but he was here in LA talking to the people and coming in, so come on up here. Thank you, Will.
Yeah, thank you.
We will print you a certificate as well. Okay, so, oh no.
He can't beat me like that and not expect me to go up.
A few words from the other general chair.
So just to make that clear, when he said we had a very heated discussion, the actual discussion was not about whether Will should deserve that or not. The actual discussion was that I said he should deserve it, because with me throwing myself down the staircase, it was actually Michael who pretty much ran this entire show. This is supposed to be a job that is split between two people, and let's just say I didn't exactly do as much as he did. He did all the job, so I was really, really strongly advocating for him, but he eventually convinced me that chairs shouldn't give it to themselves. So we agreed Will absolutely makes more sense, but I would still try to make clear he deserves a huge round of applause.
Okay, thank you. So I would also like to thank our sponsors. All this wouldn't be possible without them, so we're very thankful. We have very good sponsors. We're a small conference. If you're an academic and you go to other conferences, you know that it's really hard to survive as a small conference, but HPG has really good sponsors, so we really appreciate that, so thank you. And one more time, I think I've talked about this a lot, but yes, thank you to the committee members. In my experience, it's always great to work with good people. Yeah, you give them tasks and they just do them, and the committee has been very much like that. So I've really enjoyed working with you. Thank you all. Okay, so now we're going to transition to test of time, or should we do next year? Yeah, let's go to okay. We're going to do test of time, and then we'll do 2027.
So, yeah, sorry about the lack of preparation here. But a tradition of high-performance graphics is that every year we look back 10 years into the past, and we see what papers we had that year, and we award one of them with the Test of Time Award. And to give this some semblance of objectivity, what we base that upon is the citation count. So we have checked Google Scholar citation counts for all of the papers published at HPG 2016 in Dublin. And I'll say third, second, and first place again, and then say a little bit more about the first place. So on third place, with a total of 40 citations, we have watertight rate reversal with reduced precision and bounding plane reuse. And that's authored by Karthik Vaidyanathan, Thomas Aklide Möller, and Marco Salvi. Then just slightly ahead of that, with 41 citations, we have filtering distributions of normals for shading anti-aliasing by Anton Kaplanyan, Stephen Hill, and Angel Putney, and Aaron Lefort. And now finally, I guess here I need another drum roll. So first place with 79 citations goes to GVDB, Ray Tracing Sparse Voxel Database Structures on the GPU by Rama Hötzlein. And so what this paper did is it took the VDB data structure and it made a GPU version of it. And so I have a little prepared text here. So rendering large and highly detailed volumetric data, such as simulated oceans and clouds in movies, requires storing the data in sparse hierarchical volumes to fit in memory. GVDB brought OpenVDB-like sparse volumetric representations to the GPU, enabling fast rate reversal of movie-scale volumetric data on graphics hardware. And looking back at it from 10 years in the future, I think this specific data structure has maybe not established itself that much. I think NanoVDB is more prevalent, but the overall idea of moving these data to the GPU and making access and traversal efficient and fast, that is relevant today and is becoming more relevant. So I think it's a great contribution and it's a well-deserved Test of Time award. Thanks.
Doing to switch? Okay. Okay, hello everyone. My name is Piotr Didek, and I'm going to announce the HPG 2027. So first of all, I hope everyone has successful and wonderful conference this year. But I think it's now time to to start looking forward to next year. So the next year, we'll try to bring you to Switzerland. The conference will be organized in Lugano. So it's the south part of Switzerland. Maybe not many of you know Lugano. People from Switzerland know, but the more away you go from Switzerland, people maybe know Lugano less. It's a wonderful location. It's a wonderful city in the southern of Switzerland, on the border pretty much between Switzerland and Italy, which gives you this nice mixture, cultural mixture. And very close to the lake is the location of our conference. It's literally 5 minutes from the lake. And this will be organized at my home university, which is Università della Svizzera Italiana. Don't confuse, this is not the university in Italy, as many people think when they see the name. It's actually the translation of that is University of Swiss part of Switzerland. And we got already organization going, so we have a wonderful venue at the university, which is again 5 minutes from the lake and the city center. We have a right-sized room and all the facilities that will be provided by my university. Now, a bit about the organizational information about the dates and how you get there. So we had some discussion when to organize the conference. As you know, every 2 years, the HPG is co-located with EGSR, and this will be the case also next year. So you will get in, oops. No, doesn't work. Let me, what happened? Okay, no, I think, yeah, I think I have to, do I need to go back again? Okay, so that's the venue. Now, okay, so it will be co-located with EGSR, so you can get full week of graphics in beautiful Lugano. We did the switch, so the EGSR usually was after HPG. Next year will be the other way around, and this is because we wanted to increase the gap between the 4th of July and HPG. So the EGSR will start on 5th of July, so that's Monday, and then the HPG will start on the 7th of July. So please mark these dates in the calendar. Traveling to Lugano is relatively easy. You can fly to Zurich and take a train, 2 hours train that takes you down to Lugano. You cross beautiful Alps. You go to the other side of the Alps. You pass by the longest rail tunnel in the world, which is San Gottardo Tunnel. So very interesting trip. If you choose to fly to Milan, you can also fly there, and then you take a train, which is 1 hour, 40 minutes, and the train brings you to the center of Lugano, which with a public transportation, within 10 minutes, you're at the venue. For those who come from Europe, it's also relatively easy to get by train directly to Lugano. Within a few hours, each reachable. Just to show you some nice pictures, to get you excited, we're already looking into some venues, and we are looking forward to booking them for you. With this, I would like to finish with a short video showing a bit how the Lugano region looks like, and I want to mention that, yeah, if you want to bring your family and make holidays there, it's a wonderful location to do also this. Should be sound, but there's no sound. So very soon we'll start putting some information online with all the links, all the dates. So yeah, just to close this, I hope to see many of you in Lugano, and I'm looking forward, and I hope you're looking forward as well. Thank you.
Okay, that's a wrap. I see the lunch is there and we've finished early. So enjoy the rest of your time at SIGGRAPH.